All right, good morning, guys. Today we're going to be covering 8.6 angles related to circles. We have four learning targets that we're going to be covering. The first one, determine the measure of central angles. We've done that in 8.1 before. And then the next three learning targets are all new things for us. So I can determine the measures of inscribed and tangent chord angles, the measure of chord angles, and the measure of secant tangent, and tangent angles. So lots of different angles that we're going to be working with today. But the main thing that we're going to be wondering each time whenever we get to a problem is where is our angle in relation to our circle? So to get started, we're going to go ahead and do a little bit of a practice problem, and we're going to use a specific theorem for this practice problem. We're going to see this theorem once again as we go ahead and prove what we're going to be doing today. So our first problem is we're going to solve for x. Now, as we can see, we have a little triangle here. And in this triangle, we know that it's isosceles because both angles are the same. And that makes sense because in the circle, these are both radii, and we know that radii are all congruent within the same circle. So what I'm going to do is I need to solve for x. So the first thing I'm going to do is I know that this is a straight line because it's a diameter. And as a result, these two angles will be supplementary. So therefore, I can go ahead and start by doing 180 minus 132 degrees to give me 48 degrees as my external angle. Now, the theorem that I'm going to use here, which you'll see a little bit later today, is the external angle theorem. It states that if I have two remote interior angles and I were to add them together, they will equal our exterior angle. So essentially, x plus x equals 48. Or 2x equals 48. If I want to solve for x, of course, I'm going to divide by 2, which will give me x equals 24. So keep in mind of this theorem, we're going to be doing it a little bit later in order to prove some things that we're going to be covering today. So again, the main thing that you guys need to focus on for today is where is the angle measure in relation to the circle. Now there's going to be three different instances that we run into. It can be on the circle, meaning that our angle, our vertex, is on the circle itself. It can be within the circle, so inside the circle. If you see that the vertex of the angle that you're trying to solve for is inside the circle, it'll have its own equation. And the last one is outside the circle. If your vertex for your angle is outside the circle, it will also be given a separate equation. We're going to explore these three different scenarios on the next couple slides. And these three scenarios, each one of these will have a different equation. So we'll be coming back here to make sure that we give each of these an equation later on. So we have an easy place to find those in our notes. So the first situation that we have is when we are on the circle. So if we are on the circle, that again means that the vertex itself is on the circle. So for this first one, I have angle HKM. HKM is called an inscribed angle. An inscribed angle just means that all 3 points are on the circle. So angle HKM is an inscribed angle. The other type of angle that we're going to have is a tangent chord angle. A tangent chord angle is made up of a tangent segment and a chord of a circle. So of course we see the chord and the tangent, but where's the vertex of our angle? Well, the vertex of our angle is on the circle. It's point Q. So if you ever run into an angle that is on your circle, you will be able to find that angle because it will always be 1/2 the measure of its intercepted arc. Now, when I say intercepted arc, that's the arc that is cut off by the angle measure. So in this case, HM is the intercepted arc. And with our tangent chord angle, PQ is our intercepted arc. It's being cut off by the angle itself. So therefore, we have a couple different equations for this. We have angle K is equal to 1/2 of arc HM, whatever that degree amount is. And then we also have angle Q is equal to 1/2 of arc PQ. So those are the two equations that we can see. And of course, I tried to color coordinate it. So our angle is equal to 1/2 of the arc it's facing. And same thing over here. Our angle is equal to 1/2 of the arc it's facing. So if it's on the circle, it's always equal to 1/2 of the arc it is facing. So let's go ahead and prove this real quick. And you don't need to write down this proof, but I just want to show this to you guys. So if I'm going to prove this, the first thing I'm going to do is I want to prove that angle A is 1/2 of arc BC. So first off, I know that AO is congruent to BO because they're both radii, and all radii in the same circle are congruent. Further, if I look at angle BOC, this is a central angle. It's formed at the center of our circle. And if we recall, a central angle is always congruent to the arc that it is facing. So I can say that angle BOC is equal to arc BC. Further, since this is an isosceles triangle based upon the radii being congruent, I can therefore say that angle OAB is congruent to angle OBA. So those two angles are congruent, because if the legs are congruent, then the base angles are congruent. From there, we're going to go ahead and use that theorem that we talked about earlier. Angle A and angle B are remote interior angles. So if I add those two remote interior angles together, it will equal our exterior angle, angle BOC. Because remote interior angle sum is always equal to the exterior angle. Well, since these two angles are congruent, I can go ahead and just say that one of those angles is equal to since angle AOB is congruent to angle OBA, two of those angles are equal to angle BOC. So I'm just saying that since we have two of them, I'm adding them together. I'm saying that they're both the same angle, and that's equal to angle BOC. And on top of that, since angle BOC is equal to arc BC, I can say that 2 times angle OBA is equal to arc BC. Lastly, I'm just going to go ahead and get my angle by itself by dividing both sides by 2, and that will give us our two equations to finish off this proof. We get angle OBA is equal to 1/2 of arc BC, and also the converse, twice times the angle is equal to the arc. So the converse is also true. So all this is showing is that if I have this angle for the arc measure here, this angle measure will always be half of that arc measure. That will always be the case if we're on the circle. And I know that this says angle OBA, which is this angle right over here. But again, these two angles are the same, so it works for both of them. And again, that's also why the tangent chord angle works for this one, because again, the tangent chord, that would just intersect right here. All right, next up, what if we are inside the circle? So if I have an angle that's formed inside the circle, it's typically done by two chords intersecting. So this is called a chord-chord angle. Now, again, the important part is where is the angle at in relation to the circle? In this case, it's inside. And if we're on the inside, then we need to add. So inside means add. The measure of a chord-chord angle is 1/2 the sum of the measures of the arcs intercepted by the chord-chord angle and its vertical angle. So to make this easy, let's go ahead and say that we're trying to find this angle right here, angle P, angle CPD. Well, then what I can do is I can go ahead and say that angle CPD is going to be half of the angle that's facing plus half of the arc that's facing. Let me go ahead and rephrase that. Half of the arc that's facing plus the arc that is behind it. So therefore, angle CPD is equal to 1/2 of arc CD plus arc EF. And it will always be add when we're inside the circle. Now say that I was trying to find this other angle, then I'd add arc EF with arc CD. So again, it will work for either angle, and it works for all angles within here. If I was using one of these two angles, then of course I'd use the arc in front and the arc behind. So we can go ahead and create a general equation for this one, as my angle is equal to 1/2 times the arc in front plus the arc behind. And that's an equation that we can use whenever we're trying to find out the measure of an angle that is inside of our circle. Or if I'm given the measure of an angle within our circle, I can find one of these two arcs if I have the other one. So again, I can either find an angle here given two arcs, or I can find an arc given an angle in a second arc. So again, this opens up a lot of doors for us. The last type that we have is outside the circle. If we have our angle outside of the circle, which we see on each of these, V, C, and F are all located outside the circle, then that means that we are going to subtract. Outside means subtract. Inside means add. On the circle means take half. So the first one that we have here, this is a secant-secant angle. It's called a secant-secant angle because it's made up of two secant segments. Now, whenever we have an angle outside, our equation will always be our angle is equal to the arc that is far away, SY, minus, again we're subtracting, minus the arc that's close by, XT. And again, these are still being formed by the actual angles themselves. That's how these arcs are getting cut up. It's by this angle. So that's how we're able to solve these. So angle V is equal to 1/2 of arc SY minus arc XT. The second example that we have here, this is a secant-tangent angle. It's made up of a secant segment and a tangent segment. To find out this angle, again, we do the same exact equation. But for angle C, it'll be angle C is equal to 1/2 of the far arc, AD, minus the close arc, BD. And again, we can see that the angle is cutting up our arcs for us so that we know which ones to use. So again, that's angle C is equal to 1/2 of arc AD minus arc BD. And then the last one that we have is F. This is made up of a tangent-tangent. This is a tangent-tangent angle. Two tangents are here. And this one's going to be a little bit strange. I only have 2 points here, so when I name it, I'm going to add in an extra point. So, since this is a tangent-tangent angle, and the angle is outside, we still do the same exact equation. Angle F is equal to the far away arc. I'm going to go ahead and add in point G and call it arc EGH, minus the minor arc, arc EH. So again, I'm taking the major arc minus the minor arc. Those are the three various situations that we have. So let's go ahead and recap and give general equations to each of these. So again, the first situation that we'd have is when we are on the circle. That means that we are inscribed within the circle, and our equation is 1/2 of the inscribed arc. The second situation that we saw was when we were inside the circle. This was made up of chord-chord segments, and the chord-chord angle that we saw, the equation that we had was 1/2 arc 1 plus arc 2. Again, when we saw that we were inside, we always add. Let me go ahead and create our general formula for that one. Again, that formula is our angle is equal to 1/2 of the arc in front, the arc that we're facing, plus the arc behind. And then our outside the circle, again, we were subtracting. That's for secant-secant, secant-tangent, and tangent-tangent angles. And our equation was our angle is equal to 1/2 of the far arc, the arc that's far away from the angle, minus the close arc, the arc that's right next to us. Those are the three formulas that you should have near the top of those notes. So again, if we're on the circle, it's 1/2 the inscribed arc. If we're inside the circle, it's the arc in front plus the arc behind. And if we're outside the circle, it's the arc that's far away minus the arc that's close. Of course, we're taking 1/2 of both of those as well. So with that being said, let's go ahead and try out some sample problems. Our first sample problem, we're given that AB is the diameter of circle P. BD is equal to 20 degrees. DE is equal to 104 degrees. We would like to find angle C. So first off, angle C is outside. Outside means subtract. So therefore, angle C is equal to 1/2 of arc EA minus arc DB. But I don't have EA's distance, so I need to find that. So to start off by finding EA's distance, first off, I know that BA is a semicircle. BA is a diameter from the given, so that means that arc BA is 180 degrees. From there, I can find out what arc EA is by doing 360 degrees minus 180 minus 20 minus 104. And that will give us everything but EA here. So if we subtract all that from 360, we'll be left with EA, which is 56 degrees. Now that we have EA, we can actually solve for angle C. Again, angle C is outside. Outside means subtract. So therefore, angle C is equal to 1/2 of 56 minus 20 degrees. Well, 56 minus 20, that'll just leave us with 36. Half of 36 is 18. So angle C is 18 degrees over here. Let's go ahead and try out our next one. Given the stated dimensions, we would like to find y. So first off, I have these two arcs, 47 degrees for BC, 29 degrees for AD. I can't use those to solve for y, but I can use those to solve for angle BEC. So since angle BEC is on the inside, I know that we're going to add right away. So therefore, I can use the equation angle BEC is equal to the arc in front, 47 degrees, minus the arc behind it, 29 degrees. So angle BEC is equal to 1/2 of 47 plus 29. Well, 47 plus 29 is 76, and half of 76 is 38 degrees. But that's not y. That's angle BEC. But angle BEC and y, those are supplementary angles, because again, this is a straight line. If we have a straight line, that means that we have a straight angle. So I can therefore find y by doing 180 degrees is equal to y plus 38. Solving for y by subtracting 38 from both sides will give us y equals 142 degrees. And that's our final answer. All right, next up, we're going to go ahead and solve for y once again. So this time I have two arcs. I have 57 degrees and 31. I'm trying to solve for y. Now, first thing that we should always do is locate where our angle is at in relation to our circle. Our angle is outside the circle, and outside means subtract. So therefore, we're going to go ahead and use the equation. Angle y is equal to half of the far arc minus the close arc. So angle y is equal to half times 57 minus 31. 57 minus 31, well, that'll just leave us with 26. Half of 26 is 13 degrees. So angle y is equal to 13 degrees. Next up, we're going to increase the difficulty just slightly in these last couple problems. So the first one, we're going to find z. Well, if I look at z, z is an arc. So I'm finding an arc here. Now, what's different about this? Nothing. We're just going to go ahead and set it up slightly different from the previous one that we were just doing. So to work on this problem, we're going to go ahead and locate where our angle is. Our angle is outside. Outside means subtract. So therefore, I'm just going to go ahead and plug in my values into our outside formula. My angle measure, 32, equals 1/2 times the far arc, 125, minus the close arc, z. Again, we got these just by plugging everything in to our old equation. Our angle is equal to half of our far arc minus our close arc. From here, we're just going to go ahead and start solving. To start off, I need to get rid of this half, so I'm going to multiply both sides by 2. That'll leave me with 64 equals 125 minus z. Again, the 2 and the 1/2 are the only things that cancel over here. At this point, I subtract 125 from both sides, give me negative 61 equals negative z. Lastly, to get z by itself, I'm going to get rid of this negative out front, and I can do that by dividing both sides by -1, leaving me with z equals positive 61. So therefore, the measure of arc z is 61 degrees. And our final problem of the day, solve for y. So we're trying to find y here. Now, it's not where y is at, it's where our angle is at. So where's our angle located? Well, our angle is located inside the circle, 72 degrees right here. If it's inside, that means add. Anytime that we're inside the circle, we always add. So the equation that we're using is our angle is equal to 1/2 of the arc that we're facing plus the arc that's behind us. Well, the arc that we're facing is y, and the arc that's behind us is 21. So therefore, we have 72 degrees is equal to 1/2 times y minus 21. From here, we're just going to go ahead and solve for y. I need to get rid of this 1/2 to get started. So I multiply both sides of my equation by 2, which will leave me with 144 equals y plus 21. Again, these should be pluses here because it's adding. We're inside. At this point, I subtract 21 from both sides to get y by itself. And I subtract 21 from 144. We'll be left with y is equal to 120.